Okay, so this video is going to have lessons 6.5 and 6.6 on it. We're going to start with lesson 6.5 on page 360, independent and dependent events. Under objectives, it says calculate the probability of independent events, calculate the probability of dependent events. So those are what we're going to be learning in lesson 6.5. And then under independent and dependent events, it says Brittany has a bag containing 3 red marbles, 2 blue marbles, and 5 green marbles. She drew 1 marble but did not replace it. Then she drew another marble. What is the probability of drawing a red marble on the first draw and a green marble on the second draw? We're going to come back to that in just a little bit. But for right now, let's look at the first activity. It says multiplying probabilities. If a quarter is tossed once, what is the probability it will come up heads? So the total number of possible outcomes when you toss a quarter is 2, because there's a possibility that it could come up heads and a possibility it could come up tails. The total number of favorable outcomes when you toss a quarter and you're looking for it to come up heads is 1. Because there's one possibility that it will come up heads. So our probability that when a quarter is tossed once that it will come up heads is 1/2. Okay, number 2 says if a dime is tossed once, what is the probability it will come up heads? Well, once again, there are 2 total possibilities or outcomes, either that it will come up heads or tails, and then there's one favorable outcome that it will come up heads. Now it says make a sample space for tossing a quarter and a dime. Okay, this is number 3. So we're going to make a sample space. Remember, a sample space is simply creating coordinates for the possible outcomes. So the possible outcomes when you toss a quarter and a dime are that you'll get both coins to come up heads. So HH. You could get them to come up 1 heads and 1 tails, or you could possibly have the other one come up tails and the other one come up heads, so tails, heads, and then the final possibility is that they could both come up tails. Okay, so use the sample space to find the probability both tosses are heads. Well, as you can see from the sample space, there are 4 total possibilities or outcomes when you toss both coins. So our total number of possible outcomes is 4. And then our total number of favorable outcomes is for them both to come up heads. And as you can see, there's only one possibility here of that happening. One that is heads, heads. So our probability that both tosses are going to be heads is 1/4. So what is the product of the probabilities from steps 1 and 2? Let's find out. 1/2 times 1/2. 1 times 1 is 1. 2 times 2 is 4. So the product from steps 1 and 2 is 1/4. Now, how does this result compare with the result from step 4 here? Well, as you can see, they're the same, 1/4 and 1/4. Okay, and that is independent events. So 2 events are independent if the outcome of the first event does not affect the second event. Tossing a quarter and tossing a dime are independent events. In the activity, you showed that probability of 2 independent events can be found by multiplying the probabilities of each event. So in the blue box, it says the probability of independent events. If A and B are independent events, then P of A and B equals P of A times P of B. Let's look at example 1, independent events. A red number cube and a green number cube are tossed. What is the probability that the number on the red number cube is even and the number on the green number cube is less than 5? Under solution, it says tossing an even number on the red cube and a number less than 5 on the green cube are independent events. The probability that the red cube comes up with an even number is 3 out of 6, because there are 3 even numbers on the number cube, on the red number cube. So, and they are 2, 4, and 6. Okay, and then there are 6 total numbers. So it's 3 over 6 or 1 over 2, because 3 over 6 reduces to 1 over 2. And then the probability that the green cube comes up with a number that is less than 5 is 4 over 6 or 2/3, because there are 4 numbers on the number cube that are less than 5. There are 6 numbers total, and then 4 over 6 reduces to 2/3. Because the tosses of the red cube and the green cube are independent events, P of even red and green less than 5 equals 1/2 times 2/3. You're going to get the product, which is equal to 1/3. Okay, and you could do a sample space of ordered pairs if you wanted to check your answer. Let's look at the ongoing assessment. Okay, it says 8 cards are numbered 1, 2, 3, 4, 5, 6, 7, 8. The cards are placed in a bag. 1 card is drawn and replaced. Key word there is replace. When you're talking about independent events, everything is always going to be put back. Everything's always going to be replaced so that the events are not dependent on each other. Okay? Then another card is drawn. What is the probability that the first card is greater than 5 and the second card is divisible by 2? As you can see here, I've drawn out 8 cards. Okay? And we're going to find out the probability that the first card would be greater than 5 first. So if you look up here, greater than 5, there are 3 of them. Okay? There are 3 total. And they're these 3 right here, 6, 7, and 8. These are all greater than 5. Okay? And then our total, so then therefore our probability that the first card is going to be greater than 5 is going to be 3, that's our favorable outcome, over our total number of possible outcomes, which is 8, because there are 8 cards. So 3 over 8. Okay, now how many cards are, well, we have 2, 4, 6, and 8. Okay, they're all divisible by 2, so that's 4 cards that are divisible by 2, and therefore our probability that the second card would be divisible by 2 is going to be 4, which is our total number of favorable outcomes. Our total number of favorable outcomes over our total number of possible outcomes, which is 8, because there are still 8 cards. Okay? And now we need to, and of course, actually 4 over 8, you can reduce it to 1 over 2. Because 4 goes into 4 one time, 4 goes into 8 2 times. Now we need to, from these 2 probabilities. So 3 eighths times 1/2 equals 3 times 1 is 3 over 8 times 2, which is 16. So the probability that the first card would be greater than 5 and the second card would be divisible by 2 is 3 over 16. Now in your book on page 361 there's a typo. It says independent events again under ongoing assessment, and we're actually going to be talking about dependent events. So that should say dependent events. And so underneath where it should say dependent events, it says 2 events A and B are dependent when the first event A affects the probability of the second event B. If B follows A, then the probability of B occurring is written P, the probability of B given that A has occurred and is read, the probability of B given that A has occurred. Okay, so probability of dependent events. If A and B are dependent events and B follows A, then P of A and B equals P of A times P, which is the probability of B given that A has occurred. Page 362, example 2 says dependent events. Use the information from the introductory paragraph of this lesson about the marbles in Brittany's bag. What is the probability that Brittany will draw a red marble on the first draw and a green marble on the second draw? Let's read about Brittany's bag of marbles again on page 360. It says Brittany has a bag containing 3 red marbles, 2 blue marbles, and 5 green marbles. She drew 1 marble but did not replace it. Now, when you're talking about independent variables, you will see that things are not replaced. I just told you when you're talking about dependent variables, everything is replaced because nothing is dependent on each other. But when you're talking about dependent events, there are things that are dependent on each other, and so things will not be replaced. Then she drew another marble. What is the probability of drawing a red marble on the first draw and a green marble on the second draw? Let's look at the solution on page 362. For the first draw, there are 10 marbles in the bag. Each of the 3 red marbles is equally likely to be drawn. Thus, P of red on the first draw equals P of A, which is 3/10, because there are 3 red marbles and there are 10 marbles in the bag. Now, after the first marble is drawn, there are 9 marbles left because you don't replace that marble that was drawn. If a red marble was taken on the first draw, then there are 2 red marbles, 2 blue marbles, and 5 green marbles left in the bag. P of green on the second draw equals the probability of B given that A has occurred, and that is equal to 5/9. Now, because removing a red marble and then removing a green marble without replacing the first red marble are dependent events. P of A and B equal P of A times P, or the probability of B given that A has occurred. P of red on the first draw and green on the second draw, therefore, equals the product of the 2 answers that you just found, P of A and P of B given that A has occurred. 3/10 times 5/9 equals 1/6, and that's your probability. Okay. Ongoing assessment says Kiki has a jar with 10 red marbles, 15 blue marbles, and 25 yellow marbles. Suppose Kiki removes 3 marbles from her jar without replacing any of them. What is the probability that she will remove a red marble on the first draw, a blue marble on the second draw, and a yellow marble on the final draw? So on the first draw, you're pulling a red marble. You want to know the probability of pulling a red marble. And there are 10 red marbles, 15 blue marbles, and 25 yellow marbles. When you add these together, you'll find that there are 50 total marbles. Okay? So for the first draw, to choose a red marble, your total number of favorable outcomes is 10, and your total number of possible outcomes is 50. Okay. Your total number of favorable outcomes, because you're looking to draw a blue marble on the second draw, you want the probability of drawing a blue marble on the second draw. There are 15 total blue marbles, so for the second draw, your total number of favorable outcomes will be 15. And then your total number of possible outcomes is not 50 anymore because you did not replace this first marble that you drew. So now you have 49 possible outcomes. Okay? And then you want to choose a yellow marble. You want to find the probability of a yellow marble. So our total number of favorable outcomes is going to be 25 because there are 25 yellow marbles. Okay, and that is going to not be over 49 because, again, we did not replace either of these 2 first marbles that we drew. So now it's 25 over 48. Product of all of these. Now, 10 over 50 can be reduced to 1/5. Because 10 goes into itself 1 time and then it goes into 55 times. Okay, and we're going to multiply that times 15 over 49, and 15 over 49, and you get 15, because 15 times 1 of course is 15, over 245. Okay, and then we can't stop there. We have to also multiply that then by 25 over 48, our last probability that we figured out. 25 over 48, and that is equal 15 times 25 is 375 over 245 times 48 is 11,760. And then that reduces, 5 goes into 375, 75 times, and it goes into 11,760, 2,352 times. And then when you divide 75 by 2,352, you get a decimal like 0.03188, and it just keeps going. So you can say that the answer, the probability is about, okay, about, since it's 0.03188, and then it keeps going, you move the decimal over 2 spaces, and you get about 3.2, because you're rounding up there, 3.2%. Okay, so that's the answer to the ongoing assessment. It's about 3.2% probability of removing a red marble on the first draw, a blue marble on the second draw, and a yellow marble on the final draw. If you have any questions about this lesson, please jot them down so we can discuss them in class. And I'm going to start with lesson 6.6 right now. Lesson 6.6, populations and sampling. The objectives say that we're going to learn how to identify types of sampling and how to use samples to make predictions. This lesson is going to be pretty quick, and it's mostly just me reading as far as our video goes, and then we'll do the first activity in class, so we won't do that here in the book. But let me go ahead and start reading this to you. Under populations and sampling, it says each year over tens of billions of dollars are spent on television advertising in the United States. Companies identify characteristics of those Americans most likely to purchase their products and then ask them for the best times to air an advertisement and on which networks. Advertising professionals use the statistics generated from surveys taken about the viewing habits of American households to calculate the probability that their target audiences will be watching television when their commercials air. Methods of sampling. Surveys are conducted to gather data from a population. A population can be any group of objects being studied. Many times it is not feasible to study each member of a population, so a sample of the population is studied. A sample is a subset of a population. A representative sample contains a good balance of the objectives that make up the population. To find out what Americans watch on television and when, a sample of households and individual viewers that represent the American population at large is selected to be surveyed. There are several sampling methods that produce probability samples. A probability sample is one in which the sampling error can be calculated and where each member of a population has at least some probability of being chosen to be in the sample. The sampling error is a positive or negative number that tells the degree to which a sample differs from the population. It indicates the numerical difference between a sample measure and the corresponding population measure. Random sampling is when each person in a population has an equal probability of being chosen and each member is selected independently. If the population is a group of 100 sales managers at a meeting, an example of choosing a random sample is to place the names of each manager in a hat and draw 10 names. Systematic sampling is when the members of a population are selected according to a pattern. If the population is all those who live in a particular neighborhood, an example of selecting a systematic sample is to survey someone living in every fourth house. Stratified sampling is when the population is subdivided into groups called strata based on at least one distinctive characteristic of the population. The sample is then taken by selecting members from each stratum in proportion to the size of the stratum. For example, if the population is 100 second shift employees at a factory, the employees could be separated into the categories of 80 female employees and 20 male employees prior to selecting the sample. A randomly drawn sample of size 10 would include 8 female employees and 2 male employees. And in class, we are going to be doing this. We're going to be generating a random sample, and we're going to be generating a systematic sample and a stratified sample of the population in our class. Okay, and that's on page 367, the first activity. And like I said, we'll be doing that in class. So go to page 368, and it says the statistics from a representative probability sample of a population can be used as estimates to calculate probability, draw inferences, and make predictions relating to an entire population. Example 1, using percents. The television ratings for the 6 p.m. time slot revealed that of the 1,000 households surveyed in the metropolitan area, 325 watch the local news on Channel 2. If a company airs a commercial during the local 6 o'clock news, about how many of 75,000 television households in the area would the commercial reach? Solution says here that the sample that watched local news was 325 because that's how many watched the local news, over 1,000 because that's how many households were surveyed. And if you divide 325 by 1,000, you get 0.325. Now, the population that is likely watches local news then is 0.325 because that's what they got from their survey. Okay, 0.325 times 75,000, which is the total number, about the total number of households in the area that the commercial might reach. The total number of households. So in the area is what it is actually. 75,000 total number of households about in the area. So 0.325 times the 75,000 equals 24,375, and that's how many out of the 75,000 households the commercial would reach. Okay, so about 24,375 households will likely see the company's commercial, and that's how they figure out when and where and how to put their commercials in to things. Now, comparing samples to populations. To get a better picture of a population, researchers may collect several samples of a population. They compute a statistic for each sample and then calculate the mean. In this way, researchers can get a representative set of samples to more closely resemble the population. They can compare the statistics they calculated from the samples to the parameters of the population. Parameters are measures obtained using all of the data values from an entire population. Statistics are measures obtained using the data values from a sample. Example 2 on page 368, using parameters and statistics. In a study on water quality, an environmental group defines safe drinking water as containing no more than 0.01 parts per million of dissolved solids. The group tested 10 neighborhoods and found the following levels parts per million of dissolved solids. And then it has a table there, and it shows you their findings. Now, what conclusions should the group draw about the safety of the drinking water in this area? So you have to add all the data values. So you see they took all the data values from the table there on page 368, and on page 369 they added them all. When they added them all, they got 0.134. Then you divide by the number of data values. So if you count in the chart how many data values there are 10. Okay? So 0.134 divided by 10 then. And that equals 0.0134. So the mean of the samples is 0.0134, and because 0.0134 is greater than 0.01, the group should conclude that the drinking water in this area is possibly not safe. Now, let's look at critical thinking, and it says that the group determined that equipment that gave a reading greater than 0.0275 had malfunctioned, and those tests should be discarded. Did that change the conclusion about the safety of the drinking water? Explain. So basically what you have to do is go down to your chart and find any of the 10 numbers which are greater than 0.0275, and there's one number that is, and that is 0.03. Okay, and so you go back and you add all the numbers. Actually, I think I'll type this out. You go back and you add all the numbers that are, and disregard 0.03 in the chart. 0.005, 0.02, 0.03 we don't add, 0.009, 0.012, 0.021, 0.008, 0.011, 0.007, and 0.011. Okay, and then you just add these all together. Okay, and so I'm going to do that really quickly. Let's move my calculator over here. You guys can see it. So 0.005 plus 0.02 plus 0.009 plus 0.012 plus, oops, I put a comma there, 0.021, that should be a point there, plus 0.008 plus 0.011 plus 0.007 plus 0.011 equals. Okay, so this all, I'm going to make this point here, correct that problem. 0 equaled 0.104. Okay, and now you're going to take 0.104 and divide it, not by 10 because there's not 10 anymore, because we removed one of them because we found out that it was needed to be discarded because of a malfunctioning test. So now we divide by 9 because now there's 9, okay? And so once again, get this out, and we have 0.104 divided by 9 equals 0, 1, 1, 5, repeating basically. And so what we want to do is say that it is about, and I'll have to draw this because I can't put it on with the typing. I can't even do it drawing. Okay, about, not equal to, but about, now I can type. Oh, no I can't. Hold on guys. I'll figure this technology out soon. So it is equal to about 0.0116. And that's just rounding that decimal up that we got when we added those and divided by 9. Alright, and so that is the new conclusion. Okay. So let's see now. It did not change the conclusion about the safety of the drinking water. Okay, because the conclusion was that the water in the area is possibly not safe. And this outcome does not change. Taking the one number away because of the malfunction did not change that conclusion, because it is still greater than, the number that we have here is still greater than 0.01. 0.0116 is greater than 0.01. So we still can conclude that the drinking water in the area is possibly not safe to drink. Alright guys, and that's it for lesson 6.6 and lesson 6.5. Again, if you have any questions about either lesson, please jot them down and bring them to class, and I will see you soon. Thank you.